All right, I'm going to close this to start today's class because a couple good things have come up in some questions that people have asked in office hours, and it's just made me kind of want to go over that for everybody because I think that will help to solidify some of these ideas. The first one was going over a solution to chop left from homework 2, because I think that was probably the hardest question in homework 2. The solution is actually quite elegant. But I never gave anyone the full solution, even if I hinted that I might have given you the full solution. There was always a counterexample, or you need to be thinking about counterexamples as part of that. So what I hinted at, for those who wanted a hint in office hours, is we have some DFA for chop left. Let's first think about or remember what was chop left. So we have some language, the chop left of that language will accept every string that was accepted by the original language as long as the first character is removed from it. So how do we design, given a generic DFA, how do we design a generic DFA that answers the chop left question? So what we can expect is we have an initial state, one or more final states, and we have no idea how we get from the initial state to one or more final states. I will draw something with a single final state, but it turns out not to matter. The example that I really like to show for this is something like this, where we can branch on a bunch of different symbols. Maybe this is an A, this is a B, this is a C. Then we can come back, this is a B and a C and an A. So if we had something like this would be fairly trivial to solve for the chop left problem. If we have, think about what language this accepts. It's a finite language. There are only a certain number of strings in this language. But to do chop left of this, what do we need to do? Take the first character and lambda transition instead. So we would replace this A and B and C with a lambda transition. So we're turning our DFA into an NFA by allowing this process, but that's perfectly okay. And note that this wasn't a DFA to begin with because it wasn't a total function. There's a missing trap state and everything. So it's just an incomplete DFA. But with this, okay, great. It works for this example. Can anyone think of, besides the person I talked to about this, can anyone think of a counterexample of what form of DFA would this not work for? Yeah.
Do you have anything that loops back to the start state?
Yes. So we're going to say this loops back to the start state on an A. Now these lambda transitions are really bad because one, I'm just going to kind of leave the old letters here in. So what's a string that wouldn't have been accepted in the old language that uses this transition? Give me some example.
A, B, A, B.
A, B, A, B. We go A, B, A, B. So the chop left of this is B, A, B. So if we replace these with lambda transitions, we need to be able to get B, A, B out of this. So we lambda transition B, A, lambda transition A. There's no possible B out of the final state, so we reject. So this cannot be a solution to something like this. It turns out that the solution is a trivial change to this, or it's not quite trivial, but it's one change, but it involves a larger scale operation than just changing one edge or something of the sort. Can anyone think of what solves this problem? I can tell you two have talked about this. Maybe? No? No, interesting. All right, Hunter, what's the answer?
You make a new state so instead of the A looking back to the start state, you make a new state that points to those 3 second states with the original, like the ABC. So kind of like the original start state, you would have an A looping back to there, but that wouldn't be the actual start state.
Okay, So yeah, that would work for if there was a, but what happens if this is very large?
A lot of connections.
Yeah, you have a lot of connections to make. The easier intuitive solution that I have used is, all right, we're gonna duplicate this entire DFA. This will work. There are more efficient solutions memory-wise than this. So we're going to leave the original transitions in here. A, B, C. B, C, A. And then we're going to leave out the one loop back to the starting state. Although we probably don't want it. We can still do this. But now we're going to change this edge from pointing here to pointing here. And this allows us to basically emulate that, where only the first time that we do this are we lambda transitioning. And this allows us to actually get rid of the A and the B and the C. It's a bit memory intensive. But it's not in a different order. It's, you know, it's twice the size. Yeah. So it works. This will get you the chop left of the language. But it involved a few steps and quite a bit of thinking about how are these DFAs constructed, what rules are allowed, how do we generate something that is a bit different and weird. So that was the first thing I wanted to go over. The second thing I want to go over, this can either be today or tomorrow, we can kind of vote on this. I want it to be before the weekend and most people get started on this homework, is I want to go over a little bit more in depth of the intuition of the pumping lemma, because I think that's going to be something that a lot of people get stuck on, because there are 6 questions on the pumping lemma on the homework.
When are we gonna get homework due, Bess?
So the TA fell during the icy weather and has been basically almost bedridden for quite a while. So he just picked up the exams yesterday and is getting started with, I think got started with homework 2 last night. So I would expect that it's probably going to be next week. I always say that health comes first for students and for the TA. So I apologize, this breaks my usual promise in the syllabus of I like to have a 1-week turnaround. But it's kind of understandable, and unfortunately, I don't have time to take it off his plate, considering I'm teaching 2 new courses and I don't want to walk into class in either of my classes and say, I have no content prepared for today, I'm sorry. Goodbye. That doesn't really make your tuition worth it. So it is what it is. Unfortunately, it's kind of out of our hands, and it will get done when it gets done.
Okay.
I do apologize for that, though. It's not ideal. I would be a little bit more concerned if we had an immediate upcoming exam and you needed that feedback for the exam. Then I would be concerned, but it will be back to you well in advance of the next exam so that you can use it to prepare for the next exam.
Thank you.
All right, pumping lemma. Do we want to go over this? The answer is probably yes, because there's a.
Yes, I'm like, I'll just go over old material.
There's definitely plenty of new material we can go over. I'm reasonably prepared for this class for the near future, the next weekish. But I think the pumping lemma is something that the more intuitively you understand it, the more it will help you. So who wants to give their best shot at explaining the pumping lemma? The answer is probably nobody, but I'll ask anyway. I'm going to use the simple example because I think that it's the most intuitive example to see how this is going on, but I'm going to reproduce the construction and try to tie it as much as possible to intuition. So the simplest example was A to the N, B to the N. And so we all should know the string for this. The string that we're going to choose, but the basic 4-step process is someone is going to choose M. That is, what does M represent?
The number of characters you're supposed to traverse or whatever.
Kind of, yeah. It really represents an assertion about the number of states in the associated DFA. Player one says, I can construct a DFA for A to the n, B to the n that contains m states. So if they say something like 7, I can construct a 7-state DFA for A to the n, B to the n. Then you want to be able to provide a counterexample to that. A generic counterexample for a string will need to treat this m as a variable and not as a constant. The game we play is kind of as a constant, but the generic argument needs to be as a variable. So this step really isn't part of the proof, it's more just a part of the game. So step 2 is given m. I don't want to say find because there's too many, I guess, determine. All right, step 2, we're determining a string that's in the language with at least m characters in it. So in the game, player 1 chooses m. So we're just kind of going to say that m for the moment is 7, just for the examples that we're going to show, but you will see how this generalizes. So if m is 7, we want to choose a to the m, b to the m. Which in our example is going to be a to the 7, b to the 7. So this is the string A, B, 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 B. This is the string that's in the language A to the n, B to the n. Great. Given this, player 1 is going to go back and come up with the decomposition X, Y, Z. Who wants to or can attempt to tell me what X, Y, Z means in terms of the DFA's construction?
Is it, because there's more strings than, or more characters in the string than there are states, we have to hit the loop at some point. X is what leads up to the loop, Y is the loop, Z is what leads from the end of the loop to the final state.
Yes, yes. So the intuition behind all of this is that all interesting languages that are either regular or potentially not regular are going to be infinite languages. And what this means is there are an infinite number of strings in that language. If the language is finite, there are a finite number of strings in the language, all of those languages are regular. So we can't possibly even be asking this question, prove that this is not regular by doing this. So we could construct some kind of DFA. I like to do this kind of in a line to show it. So we have our start state and we have some final state at the end. In this case, this DFA has 4 states. What can we say about how many states we have to visit before we know we've hit the start of a loop, given that this is an infinite language? I'll even draw this out as 7. We're using 7 as an example. What is the maximum number of states we need to visit in order to know that we've hit a loop?
7.
Yeah. We don't know where this loop is, but if we've visited every single state and there is a loop somewhere in this DFA, what does it mean to go back to a state that we've seen before? If we enter a state that we have previously visited,
That's a loop, right?
that's a loop. So we can only visit each state for the first time once. And we can only, if we visit a state a second time, then we know that we've started the loop process. So we can be at the beginning of the loop, guaranteed by the time we hit M, the number of states in the DFA. So somewhere in this process, there's a loop back to somewhere else, somewhere, maybe it's here. Maybe there's multiple loops, but by the time we have gone M characters into the string, we'll start visiting states, because in a DFA, we consume 1 character per transition. So by the time we've consumed M characters, 1, 2, 3, 4, 5, 6, there are M minus 1 transitions to get you to all of those states. So by the time you've consumed M characters, you are back to some state that you've been to before. It must be. So that's the intuition behind the breakdown of X, Y, Z. In this case, let's actually draw this a little bit closer to the middle. Let's draw it here. Not quite closer to the middle, but in this case, X is going to be from here to here. This is X, the process that leads you up to the beginning of the loop. So if we wanted to write this in terms of the states that you visit, if this is state Q0, 1, 2, 3, 4, 5, 6, then X would be the breakdown 0, 1, 2, 3. Y is going to be defining what it means to go from the start of the loop back to the start of the loop. So from 3, which is part of X, to get us to that start of that, we can go 1, 2, 3. Every time we repeat from state 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, that is 1 cycle of the loop. So Y is right here. And then Z gets us from the finish of 1 loop to the end. So what transitions do we need to get from the end of the loop to a final state? And you can see now how when we say Y to the I, we're just saying consume these loop transitions I times. Loop, 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 loop. I equals 0, we don't do it at all. I equals 1, we go once through this loop. I equals 2, we go twice through this loop. I equals 3 times, we go 3 times through this loop. And then sum X, Y to the I, Z is guaranteed to be in the language defined by this DFA. There's nothing that says that this DFA is A to the N, B to the N, because no such DFA exists. But if we want to prove this, we can use this breakdown of any DFA with a loop to be able to show that we can produce an infinite number of strings in the language by repeating Y some number of times. And because there are only M states in the DFA, we know that X and Y have to be within those first M characters. We have to get to the loop and be able to start the loop process. There has to be some character of Y that's within the first M characters of the string. So this allows player 1, in this case, to go back and say, all right, I have M characters. I said I could construct a DFA with 7 states. That means I have 7 characters to give me X and Y. So X and Y have to come from the first 7 characters, the first 7 transitions within this DFA. So something about this set of 7 A's has to be broken down into X and Y in some way. There's no guarantee about where that is. You can construct different DFAs where this is X and this is Y, where this is X and this is Y, this is X and this is Y, etc. We just know it has to be within the first M characters. So this would continue until we have this is X and this is Y. Those are the only possibilities for X and Y given a construction of a DFA that's going to accept A to the 7, B to the 7 that has 7 states. Okay, so given all of this, what makes the most sense for player one to pick? It turns out that by picking A to the M, B to the M as our string, it doesn't matter what player one picks. But if we chose a different string, maybe it would matter what player one picks, which is why we think of this as a game. If it's a game, then player one is trying their best to thwart player two's attempt to prove that this language is not regular. So given this, we're just going to pick one of them. This one is probably the easiest one to see. So we're going to assume that player one picked this, that the first 6 characters of this is X. And then there's a loop of a single character. It's basically a loop back to itself. This would be saying that there is a loop somewhere in this where we consume 6 characters, 1, 2, 3, 4, 5, 6, and then we loop. And this doesn't necessarily have to be a final state in the final DFA or whatever, but this with an A, you loop and they're back where you started, loop, you're back where you started, loop, you're back where you started. So that's what that's saying. Somewhere in here, there is a loop back to where we started. And the idea is, if this is X and this is Y, then if we pump Y, we should be continuing to end up with strings in the language. If we pump Y here and say, maybe instead of doing this loop exactly once, we're going to do this loop exactly twice. What string does that produce? A to the 8, B to the 7, is that in A to the N, B to the N? No, you just need to find a single counterexample to show that it's not possible that the Y that they chose is going to produce something in the language. Now, if you're using 7, this is just an example of the DFA you could create. So you need an argument given M to show that no DFA could exist. So when we say choose M, and then say this is A to the M, B to the M is a more general argument that shows that whatever N you pick, this is the string we are going to pick. Regardless of the string, whenever you say Y to the I, what you're doing is you're increasing the number of A's without increasing the number of B's. So you get something like A to the M plus K, where K is this value of M that is chosen, B to the M, such that K is not equal to 0. And you can use that to show that this cannot, no DFA can exist. Regardless of the M that you pick, you pump A's, and that produces something not in the language. So for any value of M, there exists a string that is not in the language after pumping Y. And that turns out to not matter, no matter what the breakdown of this is, because Y will always consist of only A's. This entire proof hinges on this selection. If you intelligently select that string, this logic will all flow and follow. If you do not choose an intelligent string here, or you give something where there could be a counterexample, then your entire proof will fall apart or have holes that can be poked in it. So I just kind of wanted to give a full example and break it down logically all in one step, so that hopefully, I'm hoping this is the best explanation you've heard so far, because I want it to be intuitive as well. So knowing what X and Y and Z represent, and this is true in any math text or math proof. If you're reading math and you're just skipping over symbols, stop yourself. It's like skimming a book and not taking it in. You need to know precisely what all of these characters mean and stand for to be able to plug and play, to be able to produce the idea. And that's just the disgustingness of reading math language. But it's incredibly important. You cannot skip over things that are not immediately apparent. Questions on this process? Anything I can help clarify before you go do it for homework? I tried to pull a bunch of different kinds of problems so that the string that you choose is not the same thing every time. And so that the following layout of the proof changes a little bit as well, based on that string, so that you get some experience generating what an appropriate string is to produce an elegant proof. Yeah.
I'm not sure if the question makes sense, but how do I know if the string I chose looped and wasn't just rejected from the DFA?
Looped rather than rejected. So we know that A to the N, B to the N is the language. So the string that we picked has to be in the language.
Okay.
So this has to reach a final state at this point. So this cannot be rejected. So we can assume there exists a path through the DFA that consumes all of these characters.
Okay,
And if that's the case, then there's a loop somewhere, because we need to be able to produce an infinite number of A to the N, B to the N for an infinite number of Ns. So that means there's a loop in there somewhere. That's a great question.
so is the next step to then make a DFA with M number of states?
Nope. This is a purely theoretical argument because no such DFA exists. The entire reason I drew this out was just for illustrative purposes. Who knows how many states it actually has? It doesn't exist, but someone could argue, hey, M is 617. And then you would have to have a theoretical argument that says, given that there's a DFA with 617 states, it needs to be able to parse A to the 617, B to the 617, because that's in the language. If it has 617 states, then we could go through a 616 transition process, each hitting a new state every single time. So if those are all A's because of that, then that had to contain the loop, which means we need to be able to pump the loop, which means that the resulting language or the resulting string could not be in the language. So you can generalize this proof to arbitrarily large M's. But yeah, drawing that DFA would be impossible because the DFA doesn't exist for this language. But that's kind of the point of the proof by contradiction. I guess it's the one thing I haven't really gone over is the layout of the proof by contradiction. So we're assuming that L is regular. We know that it's not because the entire reason that I say something like prove this is not regular tells you that no DFA can exist and L is not regular. Some of the homework problems will, on the other hand, say something like prove whether or not L is regular. In which case you can attempt constructing a DFA for it. If it is regular, that will be possible. If it's not possible, then you need to go through this process to be able to prove that it's not regular. So we're going to assume L is regular. We're going to logic. And then we are going to derive a contradiction. So assuming L is regular happens here when we say, all right, give me a number of states in a DFA, or give me the generic numbers. There are M states in the DFA. If this is regular, then a DFA with M states does exist. We will then logic from there to say, all right, if that is the case, then this string needs to be accepted, A to the M, B to the M, by that DFA. If that DFA does exist, then according to these constraints, the length of XY needs to be less than or equal to M. And the length of Y, the length of the loop, needs to be greater than or equal to 1. The loop needs to exist. So that's the associated logic. You go through all of that and you derive a contradiction, because if we iterate that loop multiple times, we need to derive a new string in the language. So you come up with a counterexample that basically says, here are a number of times for Y that I can go through this loop, such that the resulting string is not in the language, which would not be possible if such a DFA existed. It would be possible if such a DFA existed. Since it's not possible to produce the string that's not in the language, that's the contradiction. And that's what tells us, since all of our logic was solid, the only thing that could have been wrong was our assumption that L was regular. That's the one piece of information that cannot be true, since either L is regular or L is not regular, it's binary. If L is not regular, then it must not be regular by the definition of a binary. How are we doing? Is this process kind of intuitive? There's a lot here. There's a lot here to see, there's a lot here to digest.
Give us an example of what it's gonna look like on the whole.
It would look very much like this. We would give you a language and either say, prove this is not regular. Or we would say, show that this is regular or prove that it's not. Basically, which of the following languages are regular? And then you either need to draw a DFA or an NFA or a regular expression. If you can do any of those things, then it's regular. So you have a choice of how to prove something is regular. But if it's not regular, none of those will be possible. And in order to show that it's not regular, you have to go through the pumping lemma process.
And so like if we're proving it on like a month, it's fine, just say, okay, you're going through the function, can we just say like the function on the game, we're just proving it, or you want to say?
You need a general M argument, so you can go through the pumping lemma game, but you cannot instantiate this value of M. You need to carry M through the entire proof.
So like if you were to choose a number, like you'd have to go back after and be like, so if you were to do that, change it.
Yeah, and the only change it's gonna be is this 7 will have you generate A to the 7, B to the 7. If you choose M, you need some string that utilizes M. So you're just gonna be factoring out this choice of what M is into the variable M and show how that goes through the process, which means you may need, instead of precise math that leads to a number, you may need some algebraic arguments. So like I said, there are a good few of these on the homework because I think in order to be successful on the exam, you need quite a bit of experience with this process as well as choosing this. Because there are going to be some examples of some languages that don't really adhere quite to this format. I think one of them is something like it's a prime number, or it's not a prime number, or it's not a power of 2, or some really strange language where you might have to think, all right, what is the appropriate construction of this? Such that I can show the appropriate language, that language is not regular. Questions, concerns? How can I help make you feel more at ease? Don't assign the homework, don't put it on exams. Besides that.
Okay.
Oh, just give me
Make them 0 points.
Yeah, put them on the exam and make it with 0 points. There, make them all extra credit.
Oh, there.
Make a 3 extra credit question worth the same points as the pumping lemma question.
Put it on the exam and make it negative points. If you solve this, your grade is worse.
I guess I have a final question. for
Yeah.
clarification. So, what do X, Y, I, and then Z mean?
So X is this process of getting to the loop. This is back when the loop was here. So X is the states that you need to visit or the transitions that you need to make from the starting state to reach the beginning of the loop.
Okay,
Y is the states that you need to iterate the loop once. So Y to the 1 is like 1, 2, 3. It's the states, it's the transitions from starting at 3, one pass through the loop. Y to the I means that we're going to be doing I passes of the loop. So if I is 0, we can just do X, Z, which leads us directly to a final state without iterating through the loop. X, Y, Z says get to the loop, iterate the loop, and then get to the final state. That should also be something that is in the language, according to the DFA, right? These are all legal transitions. X, Y squared Z would say get to the loop, iterate the loop again, and then get to the final state. But every construction of a string in the language is X, Y to the I, Z for some I 0 or greater.
okay,
And then we always define X as going, like we define the loop as starting with the first state that goes back to a previous state, that makes sense?
It's, yeah, starting from the initial state and getting to the loop. There may be multiple loops, but any loop will work in a DFA for the pumping lemma's purpose. So some DFA might have 20 loops.
Yeah.
Any one of them could be this Y.
Yeah, and I'm just saying, we define, sorry, like the start of the loop as the, because like in this, we go all the way to the end of 3 rather than going to just like 1.
Yeah,
The,
yeah. Because we need to be, XZ needs to be a string in the language.
needs to be 1 equal, okay.
Yeah, so we need to be able to get from X to Z, and that whole process should produce a string in the language.
Oh, okay.
That statement you just said where there could be different loops in this DFA.
Yeah.
I mean that there could be different X's essentially.
Yes, but you're only gonna use one of them in your proof.
Correct, but there's.
Yeah, there are different choices
You
to
choose.
So, first of all, this is all theoretical because this language is not regular. So there's no actual DFA for this. This is just a visual that helps us to understand that process. Yeah, yeah. So if we're doing anything with regards to the pumping lemma, we're not using a general DFA, but if a DFA were to exist for something. Like if we were using X, Y to the IZ to represent a regular language. That regular language DFA construction can have an arbitrary number of loops in it, which means that if you wanted to produce different strings in the language, you'd have to choose each one's different X, pump the Y, the Z to do things like generate every language, every string in the language. It's like trying to say, generate all of the numbers, all of the real numbers between 0 and 1. Not possible. Generate all the rational numbers between 0 and 1. That one's possible. It will never terminate, but given a particular query for a rational number, it will always produce it. How do we do that? Fun aside. How do we generate all rational numbers between 0 and 1? In fact, we can do all rational numbers in existence. That's even better. First of all, what's a rational number?
Non-infinite or non-infinite.
A rational number is any quotient of 2 integers.
Oh, God. It doesn't matter if it's infinite. Okay.
That's correct. So 1 is 0.11111111 and never finishes. Rational number because it is 1 divided by 9. 1's an integer, 9 is an integer. So how would you write an algorithm to start generating rational numbers that would eventually generate any particular rational number? It will never terminate because there are an infinite number of rational numbers, but you want to keep generating new ones. How do you do that?
Start with 2 variables.
Yeah.
Oh, yeah, I think irrational. Yes. Then you tell me it was rational.
Oh, I said it was irrational.
Oh.
Okay,
That's how.
Oh no, we have an infinite to the array. If you do something like start down this path.
Yeah.
Or I guess it'd be easier to start down this path. Numerator divided by denominator. Actually, I'm gonna change the order of this because we like row divided by column, not column divided by. So now, if you were to do something like this process would never finish. We have 1/1, 1/2, 1/3, 1/4, 1/5. This will always generate new rational numbers. But if I said, what about 4/3, we never generate it. How could we generate? How would we have an algorithm that given any particular query, we would eventually hit it? Etc. That's a process we can do. Just use 2 loops. A couple of if statements. And no matter where something is in this infinite to the array, you will eventually hit it. The process will never terminate. But given that I say, when we generate this particular really large quotient, you can tell me how long this program would have to run to get there, even if it's hundreds of thousands of years. All right, cool food for thought. Are we good with all of this stuff? Everyone have what they need from it? can always produce additional examples and come back to this process as you get started on your homework. I just wanted to maximize the chance that we're able to do the homework from the get-go. If you're not able to, it's perfectly okay. I have lots of office hours and love to help you out. All right, last time. We were in the process of converting something to Chomsky normal form. And we ended up with this answer, and I said that we were going to go over it in much more detail. I guess I should probably start with the process, huh? Process is on the prior slide. I can tell this is using RAM because it's super slow. All right. So the process we're going through is we're basically starting from a grammar that we know has a couple of things we know. There are no lambda and no productions, with the right-hand side as a single non-terminal. If this is the case, then we can convert that into Chomsky normal form pretty simply. So we just go through this process where we say, okay, we're going to make new non-terminals for each terminal. So in the example, that looks like this step right here. We're going to make new non-terminals for each terminal, and then where each terminal appears in the original grammar, we're going to replace it with the associated non-terminal that we just made. So B sub A, for instance, is the non-terminal for the character A. We're going to go through the old grammar. We're going to replace each terminal with its associated non-terminal that we just created in these three productions. Then we need to get these productions into Chomsky normal form, which only allows there to be two non-terminals in each production, on the right-hand side of each production. So here we have three non-terminals. Here we have three non-terminals. Here we have two non-terminals, so we notice that B did not change between here and here. It's the same, but some things did change about these first two productions. So let's talk about what we need to do. So we need to produce some new non-terminals that represent what I like to call the rest of the string. So we have, this is broken down here, and we see that we can immediately copy this first element, and it comes directly in the start symbol. But we can only consume one of these because we need a new variable now to represent the rest of the original start. We can't grab all three of them. We can't grab the first or the second because then the start isn't the same production, right? We need to be able to say that it's A, B, B sub A. And here we see that it's A, B, B sub A. So it's equivalent in this form, but we can't just grab the second thing. We need to grab the rest of until there are only two things left. So we're going to make a new non-terminal. We'll call this D sub 1. You can call it anything you want. There's nothing that says that this needs to be the appropriate language for it. But we'll call it D sub 1 and say that this is going to be the first non-terminal of S followed by the rest of S. And this is now D sub 1 is the rest of S. The rest of S now only has two things, so we can directly put them into that. We don't need any additional variables to represent the rest of D sub 1 because there are only two elements. Does that make sense? Similarly, we need to do the same thing for A. Since there are three elements here, A is now going to be the first element of A followed by the rest of A. So we need some new. We need some new non-terminal that represents the rest of A, which in this case is going to be this. We can say with two non-terminals, A is the first non-terminal plus the rest of it. And then we'll define D sub two to be the rest of it. In this case, there are two things left. With the last 2 minutes, I want to give a little bit of a longer example here, because I think that this process becomes more clear as you see things with more than 3 non-terminals in it.
Is in the like grammar, should the A be A on S be a capital B? Because it would seem that way from the rest of the.
No, that looks right to me.
Because you can never access B. At least in the original grammar. Or is it like, I forgot.
You can access B,
The non-terminal B.
A, D sub one, D sub one is B.
The original grammar.
Oh, the original.
Yeah.
Gotcha. Yes. Yeah, this is not, there are issues with the original grammar. That is fun.
Yeah, the way that one on the right is defined makes it seem like that B should be a capital B in the original grammar.
Yeah, it should be. I think you're right. That this should be a capital B. This looks like something that I wrote myself.
Or is that the one in S, not the one in A?
Sorry, one in S. Yeah. Yeah, this is a capital. Yeah, now they're equivalent. That's a really good catch. Yeah, this is not an image. This is something I typed myself, so it's probably my own error in copying. In fact, I should probably just make that change now. I'll do it later. Last couple minutes, let's pretend that this is a little bit longer. All right, now it's a little bit longer. So if we wanted to change this rule into Chomsky normal form, we would again need to redefine S. What would it be?
That's all incarnated, I assume.
Yeah, I got rid of the comma, and then we have A, B, B sub A, B, A, B sub C, B sub B.
AD1.
Yeah, it's still A D1, where D1 is going to be the rest of S. What's D1 going to be?
B.
B D sub 2. What is D sub 2 going to be?
B A sub three.
B A D sub 3. What is D sub 3 going to be?
B sub 4.
What is D sub 4 going to be?
You could say it's B sub B.
A D sub 5. So I mean, you can start to see how it works, where we have different levels of D sub 1, which is the rest of S after the first character is consumed. D sub 2, which is the rest of S after the first 2 have been consumed.
So for D sub 4, could we instead do B sub B, because B is already A, B sub C. And that's
Yeah,
the first two.
you can, this is a general algorithm for this. So there are always shortcuts that you can make if you find that there are some similarities in what you're producing.
When doing this process, do we want to do simplifications like that or no?
If you're writing an algorithm, you don't. There are always counterexamples where you don't want to do that shortcut. If you were going to be doing this for real to produce the shortest possible grammar, you'd probably want 2 separate algorithms, one to produce this and then one to analyze this and make it simpler. Yeah,
It removes one construction.
yes. So other questions about the process is does the process of breaking down a complex one into ones that are in Chomsky normal form make sense? Anything I can address? All right, we'll come back tomorrow and we'll just get to some new stuff. But I think this was worth it. I hope this was worth it to just go over some examples that will help with the homework. If you didn't feel like it was helpful, give me that feedback.
Yeah.
So.
I-